All right, Henrik, thank you very much for the introduction. So we'll just get right into it. So we're talking about 3D multimodal object tracking for autonomous driving. So let's get started. So everybody's here at this workshop. So everybody, I think, is already convinced that 3D multi-object tracking or multi-agent understanding is really important for the task of autonomous driving. So let's just do like a quick overview of the basic pipeline, and which I think most people are already aware of. Right, so we're going to have some kind of sensor data. We'll do 3D object detection based on that data, do some kind of data association, and then we'll usually have some kind of output, and then we're going to evaluate it. So let's start with the sensor data. So, in the autonomous driving context, we have different types of inputs. The ones that I think we work with the most in computer vision is LiDAR and RGB. But we also have access to LiDAR, GPS, IMU, so it's very much a multimodal sensor or multimodal input kind of task. Okay. Once we get this kind of data, the next task is 3D object detection, and this is an area that I think people in computer vision have really been working in a lot, and we've seen a lot of progress in. And the idea, of course, is to get the 3D bounding box of the object in a streaming fashion, in an online fashion. Right? And then the next part of the pipeline is data association. So there's many different ways to do this, but maybe one of the standard ways to do this is to get your 3D detection results, and then you use some kind of matching algorithm to find tracklets or trajectories, and then you want to associate your tracklets for long-term tracking. And then the last part is going to be evaluation. And this is a part that's really important, I think, for us as a community. And a lot of people have come up with different metrics, mostly from the 2D multi-object tracking kind of research area. Many of us are familiar with MOT-A, MOT-P. IDS would be like the number of identity switches, the number of fragmentations, and there are really a lot of metrics that we use to check for performance. Okay, good. So that's kind of a quick overview of our standard pipeline. And now let's go on. Let's see, what is the state of the art right now? Where are we right now? Okay, so start with sensors. One of the huge kind of influential factors that we've had in computer vision are the releases of really big data sets. Right, so if we compare right here, this is a snapshot from the Waymo paper. If we look at the Kitty data set, I have here highlighted in green, the 3D annotated boxes, right? We had something like 80,000 instances. Now in the biggest data sets, we have 12 million. So this is like 150x increase in the number of annotations we have. And this really has kind of energized our field and has helped us to make a lot of progress. Okay. So there are many data sets, good. So for 3D object detection, there are many kind of approaches. If we hone in just on RGB detection, like monocular 3D detection, same thing in the last couple of years, in the last 3 years, we've seen a 15x increase in performance, right? We started out, it was a really challenging problem where we were getting 2 or 3% AP. And now we've kind of brought that up into the 30s. So good. Interestingly, right, LiDAR has become pretty popular in the computer vision community. It was, in the olden days, people would try to submit LiDAR papers and they would get rejected because people would say it's not computer vision. But now, it's a modality that I think a lot of us are working with. And we've seen the same thing in the last 2 years. We've seen huge jumps, 27% increase just in the last 2 years of LiDAR or fusion-based 3D detection. And this is performance on the Kitty data set, right? So just in 2 years, we're making a lot of progress as a community. If we go on to data association or for 3D MOT, we see the same kind of increase. I guess the time span is a little bit bigger because this figure here is including both 2D and 3D MOT, right? So across the bottom, you'll see the speed of the algorithms, and then I guess the dimension I want you to focus on is the accuracy. So that's the y-axis. and there are all these different methods. So back, I think this first method that's on here is from 2015, right? Where we were at MOT-A of about 72, and now we're up past 85, right? And we've seen an 18% increase in the performance in so data association and for multi-object tracking. Okay, I put a little note here that at the bottom that the 2D, the 3D methods are kind of mixed in with the 2D methods, and they are compared using 2D evaluation on Kitty because, well, at least at the time that we published this paper from where this figure is from, there really wasn't a unified benchmark and evaluation metric for 3D MOT. Okay, good, let's go on. One of the recent trends I think that we've seen in data association, right, was kind of breaking up of the data association module into two parts, into the feature extraction and an optimization module, right? So maybe in traditional methods, you would just get your 3D object detections or 2D object detections and then put them into, you know, an optimizer like Hungarian method or some kind of tracking. Okay, but now we've seen kind of the split. This is the trend that we see, and they're typically now jointly optimized. So really, if we break down the state-of-the-art pipeline, if we go to the next slide, right, it should look more something like this. Okay, so this is kind of the basic pipeline that we're all working with in this area. And the question is, you know, as we look at this, what are the open problems when we consider 3D MOT? So throughout this talk, we're going to kind of talk about how we address some of the open problems. I have like a whole list here. I'm going to return to these at the very end. But inside of this talk, there are probably two aspects of this pipeline that we've been thinking about and that we've kind of addressed. And that's what we'll share about today, and Xinshuo will share about that. So the first one is with respect to feature extraction, right? So when you get a 3D object detection, you want to extract some kind of features. You know, a lot of the ways that features have been extracted up to now didn't really take into account things like the context of other objects or other scenes or other kind of features. And so I think this is kind of an area that's still open, right? There are many things that we can do. And then the other one, maybe it's a little bit more of like a mundane topic, but a very important one, which is some of the weaknesses with evaluation metrics for 3D MOT, right? So for the metrics for 2D MOT, those are pretty well established. But you know, what happens when you get into 3D? And might there be some problems with the older 2D MOT metrics that we could improve on? So those are the two that we'll talk about today. So I'm going to hand it off to Xinshuo, and then Xinshuo will talk about that, and then I'll come back and kind of wrap up at the end.
Okay, I think now I'm good. Yeah, it was muted and I cannot unmute myself. I'm sorry. Okay, thanks for the invitation, and also thanks for Kris giving the introduction. Now I will talk about our recent work on addressing the two open problems that Kris just mentioned. The first one I will talk about is the evaluation. How can we improve the evaluation matrix for 3D MOT method? So first, what are the issues of the current evaluation for 3D MOT methods? Well, before answering that question, let's first look at one important concept, which is the intersection of union. The intersection of union is used to measure the accuracy of the predicted box with respect to the ground truth box. And the intersection of union can be measured in either 2D space by computing the area on the image plane, or measured in the 3D space by computing the volume. And both 2D and 3D IOU are useful, but should be used in different cases. However, for the pioneering 3D MOT dataset, Kitty, the the evaluation is performed on the 2D image plane, which means that LU is computed on the image plane instead of in 3D space. So if you work on a 3D MOT system and you want to evaluate on the KD dataset, the common practice would be to first project the 3D trajectory onto the image plane, and then run the evaluation code provided by KD, which of course will give you the 2D MOT result, not 3D. So why is it not good to evaluate the 3D MOT method on the 2D image space? Well, the answers are quite straightforward. First, it cannot demonstrate the strength of the 3D MOT method. So what makes the 3D MOT method advantageous or more useful over the 2D MOT method is that the 3D MOT method output extra information. For example, the depth value or the distance or length of the object, the heading orientations. Those information could be useful to motion planning and control for autonomous systems. However, if we use 2D matrix to evaluate 3D MOT method, we are basically throwing away this information during the evaluation. And also, using 2D matrix cannot fairly compare 3D MOT methods. Why? Because 2D matrix does not penalize the wrong predicted depth values, or length, or the heading orientations, as long as we have a pretty decent 2D projection. So to demonstrate this, we put a toy example here, where we have 3 3D bounding boxes, and also their corresponding 2D bounding box here projected on the image plane, where the red one is the ground truth, and 2 predicted boxes are denoted as green and blue. So the question is, which predicted box is better? Is it blue or is it green? So if we use the 2D matrix, it's obvious here that the blue one has a much higher 2D LU with the red one, compared the 2D LU between the red and the green ones. So it's better the 2D, the blue box is better in 2D evaluation matrix. But is that true in 3D space? Well, it's definitely not. If we look at the visualization here on the right, we can see that the green box has much higher 3D LU compared to the blue one with the red ones. And the blue one has a clear wrong predicted depth value here. So that's not what we want. And the conclusion is that we should not use 2D matrix to evaluate 3D MOT method, but instead to use 3D MOT matrix. Okay, so this leads to our solution. We are basically replacing the matrix in the KD evaluation code by changing the 2D LU to 3D LU. That's simple, and we release our code to the GitHub, which received about 800 stars so far. So anyone interested, we put our QR code here for you to scan. And also, in order to advance the 3D MOT evaluation in more advanced dataset, instead of just use on the KD dataset, we work with the autonomy collaborators, and we put our 3D matrix in a new Xinshuo dataset for evaluating 3D MOT method. And we're welcome for everyone working on this topic to use that dataset to evaluate. Okay, so now we have the 3D matrix, and that's good. But are we done with the evaluation? Is there anything that we can improve further? Well, let's first review one of the important metrics, which is the multi-object tracking accuracy here, abbreviated as MOTA. We can see in the figure here that the MOTA performance is changing at different recall points, while being the highest when we choose the recall point as about 0.9 here. So we can see that the MOTA performance is measured at a single recall point, while it's ignoring all other points on the curve. Again, the common practice for using the MOTA for evaluation could be 3 steps. The first, we have to select the confidence threshold, for example, 0.9. And then we have to filter out the detections with a lower confidence than the threshold we just picked up. And then we just perform the data association on the rest of detections we still keep there. So why is it not good to evaluate at a single recall point as the MOTA performance? There could be many consequences. The first consequence is that the confidence threshold need to be tuned, actually carefully tuned. For example, if we look at this figure again, we have to find out the best confidence threshold by running loss experiments, probably on the validation data set, in order to find out the best threshold. And also, different detectors will give a different detection results that has different characteristic over confidence. So if we want to change the detector for our MOT system, that means we have to retune these parameters for the confidence threshold. The another consequence is that we cannot understand the full spectrum of the accuracy and precision. So what does that mean? What we mean here by the full spectrum? Again, we show a toy example here with two MOT systems. One is in the blue and one is in the orange. And we can see that orange one has much higher MOTA at the recall points that we find here about 0.9. While the blue one has overall higher MOT at many other recall points, despite a little bit lower performance at 0.9 here. So ideally, we think we want to obtain an MOT system that can achieve high performance on all the recall points, not just one single recall point, so that it can be robust to all detectors and on different data sets. Okay, now we know the MOTA does not take into account of the confidence. So what do we do? Well, we simply compute the area over the curve here as demonstrated in the shadow of the figure, which we call this value as the average MOTA. This is very similar to the average precision that is widely used in the object detection task. And by computing the performance at all the recall points instead of just a single recall point here, we can now model the full spectrum of the MOT accuracy. Okay, now we're done with the evaluation, and we have a few new metrics that could be useful. And we will move on to discuss about our recent work on improved feature learning for 3D MOT, which described by Kris, one of the key components for 3D multi-object tracking method. So first, let's review the goal of the feature learning. We want to learn discriminative features for different objects, which could be useful for the optimizer to output accurate trajectories. So we found two observations in the feature learning of the current method. The first, we observed that feature extraction is independent of different objects. For example, prior work often uses 2D CNN to extract the appearance feature for each object independently, or use LSTM to obtain the motion feature. So why is this not good? Because there is no communication between object features, or in other ways, we are kind of ignoring the context information to some extent. And also, prior work often use features from one or two modalities. For example, it could be 2D appearance or 2D motion, 3D motion, or 3D appearance. Although each of these features could be useful, but it does not utilize all the information that are available. And those different information could be complementary to each other and improve the performance. Okay, now we know the issues. How can we address them? At the beginning of this project, we start by asking ourselves two questions. The first one is that, shouldn't the feature depend on the context of other objects? Shouldn't we encode the context information? Well, the answer is yes, and we proposed a novel feature interaction mechanism here. Well, the purpose of this feature interaction is clear, which is to propagate information from each object to all other neighboring objects. And we do this interaction iteratively in many layers so that we can encode enough context information. Then another question we ask ourselves is, how can we utilize the information from all the modalities? This one is a little bit simpler because we can just use a combination of different features that we have. basically using all the networks that are available to us to encode different types of features, which include a combination of motion appearance from both 2D and 3D space. Okay, now we have talked about the ideas, but is these ideas really useful, or are the strategies that we're using, for example, the multimodal feature extraction, really useful to improve the performance? First, we look at the performance by using a single feature. Here we denote A as the appearance and M for the motion feature. And we can see that if we use multiple features, or especially in the last row where we use all of the features, all of the 4 features we have, we obtain a much better performance, about 4% of improvement here, which is good. So the answer to this question is clearly yes, and we should encode different features, and they turned out to be complementary to each other and improve the performance. Then another question is the feature interaction using the GN is useful to improve the 3D MOT performance? Again, we conduct this ablation study here, while we evaluate our performance by running a different number of GN layers. Here, when we use a 0 GN layers, that means we don't do the feature interaction at all, which can be compared to our network with 3 layers of GN for interaction, and we observed a significant improvement, about 4 points on both matrices actually. So that is good also. And we think we should net object communicate with each other so that context information can be encoded to improve the performance. For more information about this CVPR work, we also have a poster session in this Wednesday about noon. So please join us to ask any questions you are interested. Okay, now we are talking about the future directions. The first one would be the end-to-end perception and prediction pipeline. Okay, as Kris just mentioned, that we now have some method, some state-of-the-art method that doing joint optimization between feature extraction and optimization. So this is useful for improving data association. But can we do further about this? For example, can we do end-to-end for detection and MOT? Or can we do trajectory forecasting and MOT? Or can we do end-to-end for all of them? Well, the answer is yes. And we did one of our recent work by implementing a joint 3D MOT and trajectory forecasting. So as we show here again, the prior work separated these 2 modules, the 3D MOT and trajectory forecasting modules. However, we think this is not good because of 2 reasons. First, the optimization of the entire pipeline is not possible, which could lead to the suboptimal performance because we cannot backpropagate the gradients. And also, since we have 2 networks, each for running a single modules, we now have to run 2 networks during testing time, which takes more time in general. So what can we do about this? What can we do to combine these 2 modules to improve the performance and the running time? The answer is to parallelize the MOT and forecasting. First, we do a shared feature learning for the 2 modules, the MOT and forecasting modules. Again, we use the GN for feature interaction here because it's proved to be useful. And we use our CVPR work as the key component for the tracking. Also, we add a forecasting head to output multimodal trajectories in the future. So is it useful to do this joint optimization? We have to prove it through our experiments. First, we show our results of 3D MOT without adding the forecasting module. And then by adding the forecasting module, we observed improvements on all of the, actually not all of them, but 5 out of 6 entries here for MOT evaluation. This proved that adding forecasting is useful for tracking. Okay, so what about the other way around? how does adding 3D MOT affect the trajectory forecasting part? Again, we first show our system without adding the 3D MOT and compare with our system by adding the 3D MOT module. We observe the AD and FD, which are standard matrix for evaluating trajectory forecasting. These two matrices get decreased. So that means our performance is increased. So this proves that our aiding MOT is useful to forecasting. Okay, so now we've proved that joint optimization is useful to both modules. And can we do further? We now have the joint MOT and forecasting. Can we do joint MOT and detection? Well, the answer is yes. And similarly, we again use our CVPR work as the component for tracking, but we add a detection hit here to output the detections based on the anchors that we predefine on the image frame. This framework can also be extended to bird eye view and 3D detection, which we haven't done yet, but it's possibly to be extended. And we will release the paper and code later. Okay, the one last thing is here is interesting is the most complete, probably the most complete at this moment for the end-to-end pipeline of the detection, tracking, and forecasting. This work is from Uber instead from our own work. So we would invite like everyone is interested could be just visit their work. We will not go into details here. Okay, another interesting direction we're going to share here is achieve trajectory forecasting as tracking. Again, we show this conventional pipeline here for perception and prediction, which has detection, association, and forecasting. So is this the best pipeline we have for the perception and prediction? Is there any other options we can possibly discover? So one of the things that we proposed in our recent work is to have this sensor data forecasting module. So instead of just doing detection, tracking, and forecasting, we first do the forecasting to obtain the future sensor data, and then run the detector and tracker on the predicted future data to obtain the future trajectories. This is essentially by switching the order of the forecasting from the end to the beginning. And if anyone is interested, again, please visit our paper directly. So I guess I will hand over to Kris again here.
Sure. I guess we're a little bit over time. So this is the last slide. So the take-home messages, the two that we want to express to everyone today is it's important to develop good evaluation metrics for 3D MOT. And we feel that there's a lot more work to be done in terms of representations of objects for 3D MOT. Some of the open problems, I can discuss these more later, but I'm just going to read them quickly. Many of the large-scale data sets, oops. Okay, English is weird here. So the data, there are many data sets, but the type of sensors and the type of annotations are all different. And that makes it hard for us as a community. So we need some kind of unified data set. 3D detection performance, we know is improving, but one of the things I think is missing is, how does it connect back to the sensor data or the sensor physics? I think that's something that a lot of us ignore, right? The optics of the sensing. Other important issues, sensor optimization, and I put redundancy here. So I think this is something that's important in industry, but really we haven't seen in computer vision work is, what are you gonna do when one of your sensor breaks? Will your system still work? And I think that's an open area of research. Yeah, detection and tracking should be coupled. The dynamics of objects, when you consider tracking and forecasting, I think that needs to be modeled with more care. We talked about representation today. And the other thing that Xinshuo kind of touched on, and one of the questions touched on, is that when we think about autonomous systems, the perception part is just one small part of the entire autonomous system, right? So once you get the perception, there's like forecasting, there's prediction, there's control, there's interaction. And really, we need to be thinking about these like multi-level optimization problems. So I think if people in industry are thinking about this, but I think maybe in our community, we we don't have enough expertise to look at the whole problem. But I think that's something that we need to do in research, and yeah, and more data sets for 3D MOT evaluation I think would be helpful. So that's it for today. Thank you all for listening. Thank you for all the people that attended.